Okay, so if you remember, we've looked at a figure similar to this before, where we have a heat transport plotted on the y-axis and latitude on the x-axis. But the figure we looked at before was just for the ocean heat transport and split up into each ocean basin. This one here is the total amount of heat transport done by both the ocean and the atmosphere. And so we see the total here in black smooth curve. And then the red is what the atmosphere is doing. And the blue is what the ocean is doing. So again, positive numbers correspond to a northward heat transport, whereas negative numbers correspond to a southward heat transport. And this is showing that heat is taken away from the equator and transported north towards the North Pole in the northern hemisphere and away from the equator to the south in the southern hemisphere. So that makes sense. That jives with what we know about where there's energy in the system and how it is, where it's moving to. And from this plot, we can see that the atmosphere is doing the majority of the heat transport in the climate system. So does the ocean really matter that much when it's doing a lot less heat transport than the atmosphere is? And I put this figure up here because just as a reminder that in the ocean, the wind-driven surface currents are doing a lot of the redistribution, the transport of heat. To answer that question, oh boy, let me pause that really quick. So to answer that question, we're just going to look at patterns of sea surface temperature when we have both atmospheric and oceanic heat transport. And this is a way of using a climate model to sort of answer a question rather than do climate projections. So climate models, which we'll talk about more about later in the course, can be useful in many ways. One of which is climate projections, but another is just trying to understand the climate system in general. So this looks pretty normal, where we see a back and forth fluctuation of the highest sea surface temperatures as each hemisphere enters in and out of summer and winter. And we see the ice melting back in the summer months and the growing and encroaching towards the equator during winter months. And this looks pretty normal. This looks what we would expect it to look like. And so what will this look like if we turn off the ocean heat transport? If we run the same model where we have seasonality and we have the atmosphere transporting the heat around, but we just shut down the circulation in the ocean and just pretend like it's a bathtub, just stagnant water. So maybe just take a moment and pause and think about, do you think the equator will get warmer? Do you think the equator will get cooler? Do you think the poles will get hotter or colder? What do you think will happen? And I won't keep you in suspense for too long. So let's go ahead and take a look at this global climate and how different it looks without the ocean transporting heat towards the poles. And so right away, we can see that the ice line is encroaching closer and closer to the equator. And if you thought that the equator would get hotter and the poles would get colder, you're not alone. That's what I thought the first time I was shown these two videos. But as we talked about earlier in the course, ice has a very high albedo. So it's really reflective. It reflects out a lot of the incoming solar radiation. And so as the ocean stops transporting so much heat towards the poles cool down a lot. And that just means that since the poles are colder, we can have more sea ice. With more sea ice, there's a greater area of the Earth's surface has a very high albedo. And so we're reflecting more solar radiation. And so this is a positive feedback loop, because as it gets colder, we get more ice. As you get more ice, it gets colder. As it gets colder, you get more ice, and so on. So this is a very powerful demonstration of a climate feedback. So I would say that these two videos demonstrate that actually the ocean heat transport is very important, because it keeps the ice line closer, or melts back the ice every year, and is more effective at doing that than the atmosphere is. And so though the oceanic heat transport is smaller in magnitude than the atmospheric heat transport, it plays a very important role in the climate system. So these are those heat transport plots that we've been looking at, with latitude on the x-axis and heat transport on the y-axis. And so this is the normal looking heat transport and atmosphere and ocean in red and blue respectively. And over here we have a pretty flat ocean heat transport. And the atmosphere, while it does increase its own transport a little bit to make up for the lack of oceanic heat transport, it cannot fully make up for it. And so the total heat transport does decrease a bit without ocean heat transport. Here is a figure of ocean heat uptake. So the ocean moves heat around, but another important function that it plays in the climate is that it actually absorbs a lot of heat, or it takes up heat from the atmosphere. There's a flux of energy, of heat, from the atmosphere into the ocean and vice versa in certain regions of the world. So there are a few places that really light up as taking up a lot of heat. So here in the North Atlantic, we have this hot spot where there's a lot of, there's a very large flux of heat into the ocean from the atmosphere. And similarly, here in the Southern Ocean, a lot of heat is being taken up by the ocean from the atmosphere. And these are regions that we talked about during the thermohaline circulation section as being locations, being regions of deep water formation. So here in the North Atlantic we have a lot of sinking water as it's getting denser and colder because it's so salty, and it sinks down. And as it sinks, it sequesters heat down into the deep ocean. And similarly, in the Southern Ocean, we have deep convection. We have water going from the surface all the way down to depth, and it's bringing heat down into the deep ocean. And then here, just to take that a step further, the ocean will take up the heat from the atmosphere, and then it transports heat around as through the current system. So the ocean is storing excess heat, but not only in the places where it's taking it up, and it's moving around due to the ocean currents. And there's a lot of storage here in the mid-latitudes as the water sinks and flows southward. And there's a lot of storage here just north of the Antarctic circumpolar current as water sinks and moves northward. So the ocean heat content, to bring it back to climate and climate change, this ocean heat content is increasing as the ocean is taking up excess heat from increased temperatures in the atmosphere due to greenhouse gases. So now we're going to start to talk a little bit more directly about climate change. And I like to ask people when they think these quotes were written. So there's this quote about the influence of the absorption of the atmosphere upon the climate. So we've talked about the absorption of radiation by greenhouse gases in the atmosphere. There's an estimation of the effect on Earth's temperature, which would be the result of a given variation of atmospheric carbon dioxide, which is a doubling of atmospheric CO2 would result in an increase in global temperature of about 5 degrees Celsius. And that's pretty close to what we think a doubling of atmospheric CO2 would result in. And so yeah, what year do you think this was written? Yeah, and these are written in 1896, which is a very long time ago. And I think a very common response that I get is that we learned about this in the 1970s, which is kind of when we started realizing like it's important to think about our greenhouse gas footprint. But we've known about the effects of CO2 since 1856, when Eunice Foote demonstrated the effects of CO2 in air on warming. And Fonte Arrhenius came up with this estimate for a doubling of CO2 would cause an increase in global temperature of 5 degrees Celsius. So we've known about this for a long time. And atmospheric CO2 levels have been monitored very accurately at Mauna Loa Observatory in Hawaii since 1958. So we have a pretty long record of atmospheric CO2. And it's been increasing steadily. So when we started measuring, the CO2 concentration in the atmosphere was 280 parts per million. Today, it's about 410 parts per million. And actually the other day when I checked, it's 416. So it's increasing by about 2 parts per million per year. Fun thing to note is that these red ups and downs are a result of seasonality. So there's more land and more plants in the northern hemisphere. So during northern hemisphere summer, more CO2 is sequestered in the biomass in plants via photosynthesis. And in the winter, it's respired out. So that's what creates this seasonal pattern. And the black line is just I think it's a 5-year average. So it's just smoothing the record a bit. And we've talked a bit about what greenhouse gases do, but the way that they impact the radiation is they absorb and re-emit the outgoing long-wave radiation. And so this figure is just showing the black body radiation curves of Earth, Venus, and Mars. And you can see that the effect of adding greenhouse gases into the atmosphere is to take chunks, basically, out of this radiation spectra. So that just means that instead of radiating along this line, like a perfect black body, the Earth actually emits a lot less radiation than one would expect because of the greenhouse gases in our atmosphere. So adding more decreases the amount of outgoing long-wave radiation. So Venus, for example, has a lot of CO2 in its atmosphere, so its average surface temperature is a lot higher than what you would expect it to be, just because it's not emitting as much is not emitting as much radiation as you would expect. So its black body radiation curve is for an object that's 260 degrees Kelvin, but its actual surface temperature is 460 Kelvin. Whereas Mars is sort of the opposite, or not the opposite, but basically Mars has a very thin atmosphere and has very little CO2 or other greenhouse gases in its atmosphere. And so it emits at pretty much its black body ideal spectra. And so its its radiation curve is similar to that of a black body at 220 Kelvin, and its surface temperature is actually 210 Kelvin. So that's a little bit colder even than what you would expect because its atmosphere is so thin. Whereas Earth's idealized blackbody spectra is that of a body at 276 Kelvin, and its actual surface temperature is 298 Kelvin, which we calculated that earlier. And that is, it's warmer than you would expect from its spectra because it has greenhouse gases in its atmosphere. So if we zoom out on our atmospheric CO2 concentrations, the Mauna Loa record that I showed is from the late 1950s to today. And so that's just showing a tiny sliver, a tiny fraction of this record. And so if we go back 400,000 years before today, there has never been a CO2 level in the atmosphere that's greater than 300 parts per million. And today we've pretty much, we've blown past that due to anthropogenic activities. And so let's take a look at the temperature response of the global mean surface temperature to that CO2 concentration increase. So this figure is showing the temperature from 1850 to 2020. And you can see that there's some variability. It goes up and down quite a bit, but it is increasing, and it's increased by about 1 degree Celsius since 1850. And this figure down here is, these are the yearly temperature anomalies, but just displayed in these colors, which I think are really evocative. It's colder than average for a while, and then it warms up. And you can see that in these colors really nicely. And actually, I misspoke a bit. It's, oh no, never mind, I didn't. So now we can zoom out on that temperature record. We have a lot of paleoclimate data. So here we are today. It's a bit warmer than it has been in a long time, but it's not warmer than it ever has been. There have been periods in Earth's history, like here, where it's been warmer or as warm as it is today. And then back here in the Paleocene and the Eocene, Oligocene, Miocene, it's very hot. And right here, this blip is the Paleocene-Eocene thermal maximum. And it was like 12 degrees warmer than pre-industrial temperatures. But one thing to notice is that this time axis is not linear. A lot of time is passing here. So these ticks are 10 million years each, but here they're only 100,000 years, and here they're much shorter than that. So what I tried to do is put this all on a linear time axis so we can better see the rate at which all of this warming and cooling is happening. And this gives us some insight as to why they made the time axis non-linear. So here's the same figure with a linear axis, and we can't even see the Holocene anymore. This is just reminding us that like the period of Earth's history that we're in is so brief. It's so short compared to the temperature record that we have here. So the warming since 1950 is less than a pixel wide, and we can't even see it. So it's really, really fast. And it's, if you can see here, even the Paleocene-Eocene thermal maximum, it took a bit more time to get that hot than it has for us here. I mean, this is like, you know, thousands of years squashed into 1 pixel. And then if we look at the projected warming from climate models by 2200, it is much more warming than we saw in the Paleocene, Eocene thermal maximum in a much shorter amount of time. So the time scale is what's really key in thinking about anthropogenic greenhouse gas concentrations and anthropogenic driven warming. And I alluded to the climate projections from climate models. Here is a figure of some of those projections. So this is from the Intergovernmental Panel on Climate Change's 5th assessment report. And here we have, there's a lot going on in this figure, so we'll just kind of walk through it. So we have time on the x-axis. On the y-axis, we have surface temperature change, global mean surface temperature change. And here in the black line is the historical period. So this has already happened, and we can validate these models against observations. And then going forward, we have 4 different representative concentration pathways. So these are different amounts of emissions of greenhouse gases, of CO2 into the atmosphere. This red RCP 8.5 is a high emission scenario. The orange and the blue are sort of middle of the road, and then this dark blue is like this utopia, we stop emitting very quickly scenario. So there's 2 main sources of uncertainty in this model. There's the uncertainty in the future emissions, or which of these pathways will be on, so the colors, and that's all from human nature. That's how much will humans emit going forward. And then there's the shading. So there's around each of these lines, there's this shading, and that comes from the uncertainty in the climate response to the forcing. So that's Mother Nature. That's how much will the climate system warm due to a certain amount of human generated CO2 emissions. So we know that the planet is warming, but where is that energy? Where is that excess energy going? It's going into the ocean, right? So here are some figures showing where the energy is accumulating within the Earth system. So this light blue and this dark blue are both the ocean. The light blue is the upper ocean, and the dark blue is the deep ocean. And then we have ice, land, and atmosphere down here as very small slivers of this accumulation pie. And here we can see even more explicitly that the ocean is taking up over 90% of the excess energy due to increased greenhouse gas concentrations in the atmosphere. And so this is just a reminder, this is a figure that we've seen before, and it's where the ocean is taking up heat from the atmosphere. And this is why the ocean is so important for climate change. It's sort of acting as a buffer for the climate system. It's taking up a lot of excess heat, but it's not really increasing its temperature that much because it has a very high specific heat, or has a very high heat capacity. So it takes a lot of energy and it takes a lot of heat to raise the temperature of the ocean. So just revisiting this map again of global temperature, how would you expect this to change with climate change? And I will answer that right away. But so here are 2 different maps of projected changes in surface temperature. This map on the left is from the low emission scenario, and this one on the right is from the high emission scenario. And there are some similarities between both of these in the patterns. So you can see right away that the Arctic region is warming the most. Also, regions, land regions are expected to warm faster than ocean. There's less warming happening in parts of the Southern Ocean and up here in the North Atlantic. And that's being mirrored over here in this high emission scenario. So we're seeing a lot more warming in the Arctic. We're seeing more warming over land than over ocean. And then there's less warming in regions of the Southern Ocean and up here in the North Atlantic. Oops, sorry. And why do we see this pattern of warming? Well, in the Arctic, the feedbacks are really important. So we talked about the ice albedo feedback. The Arctic is a region where there's a lot of sea ice, and melting that reveals the dark ocean below. So melting back sea ice results in a lower albedo and more absorption, and thus warming. The land has a much lower heat capacity than the ocean, so the land takes less heat to warm up than the ocean does. And then there's these regions where we have deep water formation. And these are places where water is sinking, so it's bringing warm water down to the deep. And climate change has an impact on ocean circulation as well. So we talked about the thermohaline circulation, and the thermohaline circulation is driven by density, which is controlled by heat and salt. So adding heat in certain locations, you can imagine, would change how the thermohaline circulation moves around. One area of active research is on the thermohaline circulation in the Atlantic, or the Atlantic meridional overturning circulation, which brings warm water northward at the surface, and then deep water formation occurs in the North Atlantic, and then cold water is brought southward at depth. And so if you're warming the North Atlantic, you're stabilizing the water column here. You're making the surface waters lighter and less likely to sink. And so there are some projections that show that this AMOC will slow down in the near future. But this is, again, an area of active research, and so it's not entirely certain what will happen. Yeah, and so that is all I have for this section.